Welcome to the video for section 6.4, and we are getting into what are called logarithms. And there's a very good chance that this is probably the first time you've ever seen these, but that's the way things go. We're actually going to be learning something absolutely brand new, perhaps, but at the same time, maybe not. And basically what we need to look at is we can have a situation like this. Suppose we have an exponential expression. We have the base raised to an exponent equals some number or some expression. Well, this is equivalent to saying the logarithm, and we show that with log, the logarithm base b. Realize that there are many different logarithms that are different bases used. And I seem to have lost my device, so let me retry it. Okay, there it's back, I guess. And so, what this is equivalent is we can take the log base b of whatever the expression is will always equal the exponent. And so these are equivalent statements, and that's basically what we are asked to do here at the very beginning. We are first asked, okay, suppose that we have the problem 2 cubed equals x, and we are asked to write this as an expression involving logarithms. So that would be log base 2, because the bases are always the same, of the other expression, log base 2 of x, is always equal to the exponent. So in essence, logarithm is just a funny way to show an exponential problem. Problems 2 and 3 ask us to do the reverse. So if we have log base 5 of 125, that equals 3. Well, that means 5 is the base, 3 is the exponent, and 125 is the other number. And this should make sense. 5 cubed does indeed equal 125. Likewise, number 3, log base b of 49 equals 2/3, which means b raised to the 2/3 power is equal to 49. And realize this is actually how we're going to have to solve these types of problems. We can solve for b by doing the necessary stuff there to get our answers. Now, the preceding problems allow us to find exact values. Log base 7 of 1/343. And we want to know what's the value. So we need to know that's going to be x. So how do we rewrite this into a form we can use? We can use exponents. So this would be base 7 raised to the x power equals 1/343. Now, basically we need to get the same bases. So 7 to the x equals 7 to the negative what? Well, I know it's negative because it's down here in the denominator, and I think if I would take 7 and cube it, that does give me 343. So now that the exponents are the same, that means x equals -3 is my final answer. Number 5, we have log base 5 of the square root of 5. First thing I'm going to do is to change this to an exponential form. So it's going to be 5 raised to the, or this is equal to x, 5 raised to the x power equals square root of 5. Well, we have to get the same bases, and square root of 5 is 5 to the 1/2 power. Now that the bases are the same, the exponents have to be equal to make this work. So the answer is x equals 1/2. And finally in this group, number 6, the natural log. Okay, here we have a little bit of a different sort of problem. Natural log, this ln right here, here my computer's acting up and I apologize. Natural log means log base e, and e is a number that we've looked at in the past, but instead of saying log base e, we just say ln, natural log. So what this means, since this is log base e, that means it's e to the x power. It's going to equal whatever's right here, e to the 4th. And it's very easy in this case because the bases are already the same, so that means x equals 4, and that is our answer for number 6. Okay, number 7 asks us to use a calculator to evaluate the expression and round our answer to 3 decimal places. So I'm going to show you where these particular things are. And first of all, realize that since we're dealing with operations in the fraction, we have to include the entire numerator inside a set of parentheses. So it's going to be log base 3. Well, log is right by the 7. So I hit log, and then I need base 3, and I need to close it out with parentheses to close out the what's called the argument for the logarithm. Plus, I need log of 2, and I need to close that out, but then I need to close out the entire numerator with another closed parenthesis. Then we're going to divide by, and then inside parentheses, we're going to do the natural log. Well, the natural log is right beside the 4, the ln. So the natural log of 3, and we're going to close out that argument, minus the natural log of 9. Close out the 9, close out the denominator, and then hit enter. And we see that our answer is negative, rounding to 3 decimal places, negative 0.708. Not really a difficult situation here. Your big problem, you just need to make sure that you include the things inside parentheses, the numerator and the denominator. Okay, number 8. We are given this particular function, and we are told that it models the average number of free throws a basketball player can make consecutively. X represents the number of consecutive days the basketball player has practiced for 2 hours, and after 42 days of practice, what is the average number of consecutive free throws the basketball player makes? Well, since X represents the number of consecutive days that he's played, and he's done 42 days, all we have to do is find F of 42. And so this becomes 1 plus 1.6 times the natural log of 43. And then it's just a matter of punching this into the calculator to go show how to do each one of these. I apologize for this. But once we find this answer would be 7.02, or in other words, 7 free throws, rounding it to the common sense rounding. Okay, 9 and 10 ask for the domain. It's very important to realize that the argument of a logarithm, like here, x plus 1, um, or this also applies for log, the common logarithm, uh, the, uh, the argument has to be greater than or equal to 0. So in number 9, we see that we're trying to find log base 3 of 81 minus x squared. So what we have to do is we have to figure out where is 81 minus x squared greater than or equal to 0. Well, we can add x squared to both sides. So 81 has to be greater than or equal to x squared. Or another way to look at it, x squared has to be less than or equal to 81. Or in other words, 9 has to be greater than or equal to x, which has to be greater than or equal to negative 9 because we can take both the positive and the negative. And so this is somewhat acceptable, but to remain consistent, this would be the range between negative 9 and 9. And we really need to have brackets because negative 9 and positive 9 are acceptable answers. Continuing, example number 10. Example number 10, I'm not going to write the entire function, I'm just going to realize that the square root of x is the function. And so that means x, square root of x has to be greater than or equal to 0, which means x has to be greater than or equal to 0. And that was stipulated anyway because square root has to be 0 or positive. And so how do we show this? Well, we start at 0 and we go forever. And so the domain of number 10 would be starting at 0 and going forever. Now we look at graphs, realize that the domain plays a huge part in the graphs because those will become a vertical asymptote is what it will become. And so that's the first thing we need to do is determine where is the vertical asymptote. And it's also important to realize that every graph, unless it's being shifted or whatever, will always go through the point 1, 0. The parent graph will go through 1, 0. So this is the way parent graph looks like for logarithm. We know it goes through the point 1, 0. Y equals 0, or I'm sorry, x equals 0 is a vertical asymptote, and what it looks like is it'll go through 1, 0, and then it comes out and starts to look like a square root, but it's not. It's a logarithmic graph. And so this is what the parent function looks like. Now we're going to do our shifts and all those other good things that we need to do. So number 11. Number 11, we look at it, and a couple things. Sorry, I lost it again. It's going to be a long video. I apologize once again. We look at the graph and we see a couple things. First of all, it does appear like it has been reflected somehow. And it also looks like it has shifted. Now, all of the possible answers given there, the shift does not necessarily show up because the shift has really only gone, well, no, it actually has, never mind. First off, by reflecting this way, that means it's been reflected over the y-axis. So what that means is my x has to be negated. So that means it could be A. Well, in fact, that's the only one it could be, because my x has to be negated. Notice in B, my x hasn't been negated. C, it hasn't. And D, the logarithm, but not the x, has been, oh, wait a minute. Whoops, the log of x has to be negated. And so that doesn't allow for a, that has to be d. The log of x has to be the one that's negated because um, log of x, you can't just separate x. If you negate the logarithm, then that means it will reflect over the y-axis. If you oh boy, you know what? Number 11, none of the choices work for what we need. And here, this is very typical of what happens with students. First off, if we look at the vertical asymptote, that's where we want to start. The vertical asymptote. Vertical asymptote certainly appears to be x equals 3. And so which ones allow for that? That would be A, B, and that's it, because C and D, the vertical asymptote would be x equals 0. So we know we're now down to A or B. Now, going this way means there is a reflection. What has to be reflected, or what causes a y-axis reflection, is the negative x. And between A and B, the only one that has the negative x is A. Now, we could have used the initial argument, as I said before, that A is the only one that had negative x to begin with. And so A is our answer. Sorry for that confusion. Too many students in the years have caused that same confusion. Now if we look at number 12, this time I promise I will do it in the logical order, which is look at the vertical asymptote to begin with. Vertical asymptote is y equals or x equals 0. X equals 0 is the vertical asymptote. So that means the argument has to just be either x, potentially negative x. We'll have to take a look. So that doesn't really throw out any of them. This, compared to the mother function, or the parent function, is a reflection over the x-axis. So that means the x cannot be negated. So that has to throw out b and c. So that leaves only a or d. Then the question becomes, if it were a, the log of x would look like this. That's the parent function. So it can't be a. D is the only one. It's negating the logarithm of x. And so 12 is D. Example number 13. Example number 13, we look at the vertical asymptote. It is x equals 0. This is very poorly drawn, but it gets the point across. So since it's y equals 0, that means x has to be, or the argument has to be x, or negative x. So that doesn't really throw out any of them yet. Okay, we see that it's reflected this way. It's reflected over the y-axis. So that means x, the argument, has to be negated. Well, that throws out a, that throws out b, and that throws out d. Only answer is C. So see, if you look at, most of the time, if you look at where is it reflected, and what is the vertical asymptote, you don't have to worry about any shifts. Almost. That's almost always true. Okay, now with that in mind, let's go to number 14, which actually asks us to graph the function. So we get f of x equals 2 minus the natural log of x plus 4. Now the first thing I need to do is find the vertical asymptote. Vertical asymptote would be set this equal to 0. X plus 4 equals 0 means x equals negative 4. So I've got a vertical asymptote at x equals negative 4. That, in essence, is your shift, your left or right shift, okay? Now this negation here, since it's negating the logarithm, then that means it's going to reflect over the x-axis. And then this 2, if this bothers you, put negative natural log of all this plus 2 out here, and you've got an equivalent statement. This would mean go 2 up. So with that in mind, let's draw in everything we need, and then it should come out okay. X equals -4. There's our vertical asymptote. We know we're going to reflect over the x-axis, so instead of going like that, it's going to go like this. Once again, instead of going like that, it's going to go like this. Now, normally, away from our asymptote, 1 over, we go through 0. But we're told we have to shift it up 2. So that means we're going to go 1 of our asymptote in this case, and 2 up, and that's the point that we're going to have to go through, is right there. And so we're going to draw the thing, and eventually it will cross the x-axis out here quite a ways. But realize that I'm really looking forward, do you have the asymptote and do you have the critical point there? You know, normally it's 1, 0, but that means it's 1 to the right of our asymptote and 0. This one told us go 1 to the right of our asymptote, but also we had to go 2 up. Number 15, we're going to do the same analysis and then just draw a rough sketch of whatever we end up with. Get f of x equals 1/3 of log base 5 of x. Okay, first thing, the vertical asymptote. Well, we just set this equal to 0, x equals 0. So our vertical asymptote is the y-axis, x equals 0. This tells us, so whenever the y-axis is our vertical asymptote, we know it's going to go through 1, 0. So that's pretty simple. And then 1/3 just simply means it's going to compress. So we think of a normal logarithm looking more or less like this, so it's just going to become even more flat. So it's going to come up here like this, and then, whoops, then it actually flattens out very quickly after that. Whether or not this is 1/3, you know, I'm not really, I want you to get the reflections and the shifts and everything else that needs to go there, okay? Continuing, and actually we're on the downhill slide. It's not too much farther to the end, thankfully, because my tablet is causing problems. So the sooner we can get out of this video, the sooner, the better it will be. So let's go to number 16. Number 16 through 18, we are asked to solve the equation. So let's see what we've got. Log base x of 3/4 equals 1. Now we can't deal very well with logarithms. Now there are times when we actually have to do logarithms, but for right now, what we're going to do is we're going to turn this into an exponential. So that means the base is x, the exponent is 1, and that's going to equal 3/4. All I've done is change from logarithm to exponential. Well, x to the first equals 3/4 to the first. So since the exponents are the same, that must mean x has to equal 3/4. Not too much of a problem on that one. Number 17, log base 8 of x squared minus 7x equals 1. Once again, we have a logarithmic equation. We need to change it to exponential. So that would be 8 to the first power equals x squared minus 7x. Well, this one's not too difficult. 8 to the first power is 8, and so this gives us x squared minus 7x minus 8 equals 0. So I'm going to factor this. This is x minus 8 times x plus 1 equaling 0, and then set each one of these equal to 0. X minus 8 equals 0, so x equals 8, or x plus 1 equals 0, or x equals negative 1. Now we do need to check here to make sure it's in the domain. So very quickly, if I plug in an 8 here, 8 squared is 64. 64 minus 56 is 8. That one works out okay. Let's try negative 1. Negative 1 squared is 1, minus 7 times negative 1 is a positive 7. So 1 plus 7 is 8. So the domains aren't violated here. So the answer would be x equals 8 or x equals negative 1. Number 18, the final one in this group. Number 18, we have the natural log of the square root of x plus 2 equals 2. Now here we get to cheat a little bit, because natural log, since it deals with e, there's a very good chance that we're going to have e as part of our answer. So we need to rewrite this into its exponential form, which is e squared equals the square root of x plus 2. Now we need to get rid of this square root, so let's square both sides. So e squared squared would be e to the 4th equals x plus 2. And our main goal is to solve for x. So x, all we have to do here is e to the 4th minus 2. Now, are we going to find an approximation? No. E is a number very similar to pi. If we have pi in our answer, unless we're told otherwise, we want to keep it there. E is the same rule. So x is going to equal e to the 4th minus 2. Okay, 19, we get our first word problem. We have a rock concert and we have 120 decibels, and we're told the decibels is, or L, the loudness, is equal to 10 times the logarithm of x over I sub 0. And I sub 0 is 10 to the negative 12 watts per meter. That's the lowest amount that can be heard. So the music registered at a loudness of 120 decibels. The human threshold of pain is about 130 decibels. So we need to compute the ratio of the intensities with its two loudness. Okay, so basically the first thing we have to do is find when does it, what is the intensity x at 120 and then at 130, and then compare the two. So 120, run that one first. Okay, setting this equal to 120, 120 equals 10 logarithm of x over 10 to the negative 12. I'm just going to put that in now, because that's what I sub 0 means. Divide both sides by 10. So 12 equals the log of x over 10 to the negative 12. Now, we're in a logarithmic problem, and by the way, if there isn't a base here, it's understood to be a 10, okay? That's called the common logarithm. If there is no base here, it is understood to be 10. So this becomes 10 raised to the 12th power equals x over 10 to the negative 12. And then to solve for x, what we need to do is multiply both sides by 10 to the negative 12. Well, 10 to the 12th times 10 to the negative 12 is 1. So that's what is x equals 1 whenever there's 120 decibels. Now, whenever there's 130 decibels, let's see how that changes. We first of all set it up in exactly the same way. We do the exact same thing, in other words, divide by 10, so we get 13. 13 equals the log of x over 10 to the negative 12. Since there's no base here, it's understood to be a 10, so it's 10 to the 13th power equals x over 10 to the negative 12. To solve for x, we're going to multiply both sides by 10 to the negative 12, or in other words, x equals 10. So what's the ratio? It's 10 over 1. The ratio is 10 to 1. So between 130 decibels and 120 decibels, the intensity is 10 times as great. Decibels are on what are called a logarithmic scale, as is the Richter scale, but I am actually going to throw out number 20 due to the convolutedness of the problem. So we're going to throw out number 20, and we will end with number 21. Final example, number 21. We have pH, and this is the pH that you have heard of, is the negative log base 10, I'm not going to put that, of the hydrogen ion, and we need to find H positive if the pH is 2.4. Well, this is just to substitute in 2.4 here and solve. So we get 2.4 equals the negative logarithm of the hydrogen ion. Negate both sides, so negative 2.4 equals the log of H positive. And now, since I didn't put it here, but they did, it's actually a 10, common logarithm, then we know it's 10 to the negative 2.4 is equal to the negative 2.4 is what the hydrogen ion is. And it does have decimals, so that allows us to go into decimals. And if we put in 10 to the negative 2.4, we see that the hydrogen ion would be 0.00398. And once again, I want to go with 3 non-digit zero numbers to determine how far do you carry this out. And so the final answer, 0.00398.